the speakers for today. This is the paper session on performative music AI systems. And we're going to have 9 5-minute long lightning talks. And please don't ask questions. You can do that in the paper session, so take notes. And yeah, the first presentation is going to be on the paper Bela-IREE, an approach to embedded machine learning for real-time music interaction. The authors are Ezra, Victor Shepardson, Jack Armitage, and Thor Magnusson. And the author presenting is going to be Victor Shepardson. So.
I want to open this in tab. That'll work. How's that sound? Sound good? Alrighty. Hey, yeah, so this paper is called Bela-IREE, an approach to embedded machine learning for real-time music interaction. I'm Victor Shepardson. This is mostly the work of Ezra from Carleton University in Ottawa. I did a small part of it and advised on the needs of machine learning framework users. My colleague Jack Armitage advised on the needs of Bela users and did a lot of the publication. And our PI is Thor Magnusson. And thanks to Bela, Beagle Board, ERC, Google Summer of Code for funding and support. Use of real-time AI and machine learning process in creative technology is increasing, and music interaction and digital musical instrument design are not an exception. There are a lot of challenges in achieving good performance for the large neural networks that are popular in machine learning these days in embedded systems, with lots of frameworks and approaches flying every which way. In this work, we tried to make some sense of the IREE project in combination with the Bela embedded maker platform, which many of you are familiar with. IREE itself is kind of this octopus machine learning compiler, which is meant to take in inputs from all the machine learning and tensor math frameworks like PyTorch, TensorFlow, JAX, so on, and then output machine code or kind of runtime specs for everything from GPU servers to laptop CPUs to mobile devices to embedded stuff such as Bela. So what we did is made a workflow and a set of tools for exploring the use of IREE to compile machine learning models down to Bela. And specifically, we made a container environment for Bela, an IREE runtime project for Bela, and something called an embedded model zoo. So first of all, that container is just a Docker image like you might work with on Bela, which you can launch from VS Code with a Bela connected and start running stuff on the Bela in your terminal. It contains the toolchain for compiling the image and toolchain for compiling Bela-IREE projects, and the utilities we made for benchmarking and profiling. Using it looks something like this, where in these 7 lines of shell stuff, you've built all these machine learning models in our zoo, compiled, benchmarked, and profiled them all on the actual device. The runtime component is a Bela C++ project, which incorporates the IREE runtime itself. So you can kind of use it like a processing block in a typical Bela program to run your exported machine learning model. I won't get into the details here. Find this at the poster session. There is, note quickly, there's also a emit-C version, which uses no IREE runtime, but just compiles down to C files. But we found the IREE runtime kind of the more useful option. And then our results, no, sorry, this is actually about the part 3, the embedded ML model zoo. That is just a small Python package which defines a whole bunch of small like neural network blocks, just meant to be a starting point for kind of developing any block you might want to use in a project in different frameworks, including PyTorch and JAX, and then exporting them through the various routes that are possible to eventually get them into IREE and finally compiled down to the Bela. So these aren't trained models, they're just randomly initialized kind of model blocks. But the concept here, I'm going to actually skip over this. Oh yeah, right, I do want this slide. Sorry. The concept here is to give you kind of this bird's eye view of what's possible on a particular hardware, specifically on the Bela, by letting you throw all these bits of models and see, like in this very nascent ecosystem, what works well, what works badly, what doesn't actually work at all, and currently like exposes bugs in the tool chains. So instead of like kind of developing your machine learning model, then running into this horrible like nightmare of trying to port it onto the Bela, you can start your project with an awareness of kind of what blocks work, what works well. You can kind of design your architecture around what's going to run in the envelope you have, and then try to train the best model you can based on that. And the flip side of that is the performance profiling, which is also part of this image, which gives you this zoomed in view where you can then find out, you know, why is this take 2.5 seconds per iteration? Which is the operator that's taking so long? Can I replace it with something? So together, these are meant to give you a very powerful kind of view into what's actually happening on the actual Bela hardware before you start your designing your machine learning models. And yeah, find us at the poster session to talk about future work. That's Bela-IREE. Thanks.
We're just going to make sure the streaming is all set up correctly. But the next paper is going to be NeuralNet, a pure data external for the creation of neural networks written in pure C. And the author and presenter is Alexandros Drymonitis.
Hello, everyone. Okay, I had a presentation mode in mind, so the bullet points are gonna be coming one at a time. Anyway, so I'm Alexandros Drymonitis. I'm an independent scholar, and will present the paper NeuralNet, a pure data external for the creation of neural networks written in pure C. So, no bullet points. So, what is NeuralNet? There you go, the first one. It's a PD external object for the creation of densely connected feed-forward neural networks, also known as MLPs, multi-layer perceptrons. It's written in C without any dependencies. It means that you don't need to import any PyTorch, libtorch, or anything into the object. Everything is written from scratch. The layers, the activation functions, the loss functions, the optimizers, everything is written in C. This is a result of translating Python code to C from the code of the book Neural Networks from Scratch in Python, which builds an MLP in pure Python by using mostly NumPy. So there was quite some reverse engineering in that aspect because NumPy does a lot of its workings under the hood. Other than that, it was a manual translation from Python to C, incorporating the pure data API, of course. Concerning related work, there are a few PD projects that build neural networks. One is the FAN object that builds on top of the FAN library, fast artificial neural network. This library is written in C, so FAN is very relative to neural net in this respect, but FAN is used only for classification, Then we have the MLlib library for PDM Max, and it's an object with the difference that the entire MLlib is written in C++, which is a bit more involved process to compile the object for pure data, as C is the native language of pure data. Plus, the an object allows for one hidden layer only. Of course, the Flucoma ecosystem, which is much, much bigger than what NeuralNet is, it's for PD Max and Supercollider with many objects for many different tasks. But it does include the neural networks and deep neural networks. So in this respect, it's somewhat relative to NeuralNet, plus it's sort of contemporary, as this project was concluded by the same time I developed NeuralNet. And there are some projects that build neural networks as PD patches, whether this is the entire process is a PD patch or whether you load neural net that has been trained at MATLAB and then you run it on a PD patch. So in this image, we can see the actual neural net object and some messages that here you can create input layer, two hidden layers, and the output layer in regression mode, so the activation functions, all except for the input layer. So ReLU for first hidden, ReLU for second hidden, and the last layer, it's a linear function, linear activation function. Yes, the loss function is mean squared error. They set the optimizer to Adam. You can add training samples by adding values as many as the input and the output neurons, so 7 values in total, for example. You can train the network and you can use, for example, a percentage of the training data sets for validation. You can validate the data set. You can get predictions by providing input values, save, load a model, and you can even morph between different models. And I'm going to play a couple of videos now. Where are they? This is the one. So this is NeuralNet getting input from the mouse pointer. So before I go on, it takes input from the mouse pointer coordinates and controls 20 parameters of the synthesizer. So 2 inputs to 20 outputs, and then the next video demonstrates the morphing feature. So you can morph between 2 networks that have the same structure, the same number of layers and neurons in each layer, same activation function and everything. Yeah, it needs a bit of optimization, this feature. And lastly, an audio file that takes input from my voice, pronouncing vowels, and it classifies as vowels and plays frozen instances of text-to-speech produced with F-Lite. This takes input from the Flucoma object that produced the MFCC of the input, and it's inspired by Flucoma examples. Let's see. I don't know how clear that is. You can check it all in the poster session. Thank you very much.
Thank you, Alexandros. The next paper is going to be NeuralMidiFx, a wrapper template for deploying neural networks as VST3 plugins. And the presenting author is Behzad Haki, and the other authors are, Julian, Lenz, and Sergi, Jorda.
So hello everyone. Can I make this full screen somehow? All right. So my name is Behzad, and this is Julian, my colleague. We are from the Music Technology Group in Barcelona. I'm doing my PhD there with Sergi Jorda, who's here with us right now. And Julian was a master's student who was working with us, and he actually just graduated. All right, what this work is about, this is basically a juice-based wrapper that we've made specifically for deploying neural networks that work with symbolic music within a plugin environment. And this work is specifically targeted for researchers, so the aim of it was to allow researchers that work with symbolic music to be able to actually deploy their models in a way that is easy for non-technical users to interact with them. So the story behind it is that, in fact, this wasn't it's not the main focus of my PhD. I'm mostly focused on real-time drum generation, and we constantly work with musicians. And one problem that I faced from early on was that we need to somehow actually share our tools with musicians so that they can interact with them and be able to actually run it on their own. So initially I had these pure data interfaces with some Python backend that they would use to run the systems, but actually it was very hard to set it up for them, and even myself, not using them for a while, going back to it, I had difficulty running it. So for me, it was kind of unavoidable that I have to make a self-contained VST to be able to actually use it in to be easily able to use this. I didn't know any C++ or Juice at the same time. It was, so it took me almost a year to do that, and once I was done, I realized why almost nobody does this, because it's very time consuming and we don't have the resources to do that. In that year, I wasn't able to do any research. It was just building this tool. So in the end, I had the idea that maybe a lot of these things can be automated. So that's how we came up with the wrapper. I'm not going to talk about the technical stuff here. We can definitely chat about it more during the poster session if you are interested. The only thing that I'm going to say is that the main idea behind it is that it tries to allow you to focus on the deployment aspect, the more model-related and the model-related aspects of the deployment process, rather than dealing with how a plugin works, how you should interact, how you should actually develop a plugin. So it tries to kind of create an environment that is very clear what the objectives are that you need to be focused on. So if you are interested, we can talk more about it during the poster session. Thank you.
Next up, we'll have an online pre-recorded presentation. So I'm just going to set that up. Where is the downloaded folder? I think I can just put one on side by side. So, this is on the drive. Thank you. Yeah, the PDF on the
Hello everyone, I'm Nádia. Hello everyone, I'm Nádia, and I will present our paper, Exploring Latent Spaces of Tonal Music using Variational Autoencoders. The research for this paper was conducted in collaboration with the University of Porto and Inestec. Our study departs from two main takes. First, the literature has shown that the musical encoding result has many implications in the performance of generative models. Secondly, these latent spaces that derive from machine learning models have cognitive and semantic value. And so, we decided to explore 6 encodings. The 4 upper ones, very common in literature, and the 2 new ones, based on the DFT and on their potential to create novel content within styles and their capacity to expose cognitive pitch relations. As a machine learning model, we adopt a flat baseline recurrent value, as it is aligned with the state-of-the-art in generative music, and its latent space has been shown to capture cognitive pitch relationships. In this slide, you can see more information on our fine implementation. In this research, we pursue 2 main evaluation strategies. The first one assesses how well the generated music captures the qualities of the trained corpus by pursuing traditional machine learning methods. The second one was proposed by Lenz and tries to understand how well the latent space captures the pitch relations within circle of fields, which is a recurrent key pitch representation in cognitive studies. We adopt the box corrals as our evaluation datasets. Here is our main takes. In terms of performance, ABC and NeuralMidiFx stands as encodings that best capture the qualities of the training data. The latent space of the proposed pitch DFT encoding shows greater alignment with the circle of fields. If you are curious about our methods and results, please come by our poster and ask us some questions. In the future, we hope to conduct an in-depth analysis of data reconstructed using pitch DFT encoding and experiment with different time-step segmentation. For example, use different segmentation per encoding. Also, we hope to explore less structured harmonic or pitch systems like modal and mimic tonal music, given the lack of available pitch spaces for these non-tonal music expressions. Some references for our work. So, we are at the end of our presentation, and before anything, thanks for your time, and we hope you have a continuation of a great conference. We provide 2 platforms for you to explore. The first one provides the code for our framework and the models we use for getting the results for this research. And the second is an interactive platform for you to explore our symbolic music embeddings, and you can actually listen and see the different embeddings for different music, and we invite you to explore it. And if you have any questions, please come by our poster and ask them. Thanks again for your time, and have a great conference.
Thank you to Nádia for presenting on Zoom. Next up, we'll have Emotional Machines. The authors are Jorge Forero, Mónica Mendes, and Gilberto Bernardes. Or not? No. No, okay. We'll have Finetuning Rolypoly tilde 2.0, an expressive drum machine that adapts with every performance, and Grigore Burloiu is going to present.
Thank you. Hello. So I'll be presenting a demo of this object called Rolypoly. It consists of a max object that is loaded with a drum track in the form of a MIDI file. And it listens in real time to a musician playing together with the drums. And also on the signal level, it generates the hits, which are timing and velocity expressively adjusted. And I also have this generate toggle, which basically deviates from the written score and starts generating on the fly or improvising. Yeah, at the demo session, poster session, I can run you through everything and you can try it yourself. So, as I said, it reads a drum track. It anticipates and reacts to your playing, and I'll show how I try to implement that. And after the performance, you can fine-tune the model to how you played with it. And it's along three directions. One is it adjusts its velocities to the velocities in the score, coming from the MIDI the big MIDI data set from Magenta that it's pre-trained on, so it goes through towards your score, and then the timings it can match, like to follow what you played. And also, this is the most interesting part. It can, it always tries to anticipate where your timing is gonna fall. So it will try to minimize its anticipation error. So that doesn't mean it tries to play exactly as you're playing, but it tries to, I don't know, find a common dynamic with you. And as I said, it generates auto-regressively hits on the fly. This is kind of the most recent and experimental feature, and I'm still working on it, but yeah, you can play with it. Yeah, this is kind of a quick diagram of what happens at runtime. It's not so easy, as you can imagine. It's not just about running inference once, but it's about having a thread of running the model while the playhead is actually moving and you're generating notes, and you have to bear all this in mind. So it's a bit of a headache. And it's all coded in C++, so libtorch. I went through phases of having first a Python to OSC to Max. Then I did it in Torch script, and I dismissed all of them for different reasons, and we can discuss why this happened at the session. But yeah, in the meantime, I'll look forward to looking at it together at the demo, and you can, of course, download and try it yourself. I will have a Mac build as soon as possible. Right now it's just Windows. And yeah, I'll be writing a couple of blogs on my website about it, because yeah, there's all sorts of strange stuff that I don't even understand. So if people are more cognizant of libtorch and stuff, I'll be glad to discuss, and transformers and all this stuff. Yeah, thank you.
Thank you, Grigore Burloiu, for presenting. That was the end of the main paper sessions, and we have 3 more presentations of the Alt-AIMC posters. First up is AI in live coding environments, Pandoras Dream. The authors are Celeste Betancur Gutierrez.
transition here. Okay, so first of all, let me do this. The paper is called AI in Live Coding Environments, and this is a case which is Pandoras Dream, a platform which is being tested right now. You can find me in that email. I came from this place, which it's a very interesting place to be doing this kind of stuff. So first of all, the idea is a conceptual thing talking about what's Pandora's box, which is kind of this surprise thing that can just be whatever. So Pandora, it's a framework that can run a bunch of different things that you can, that maybe are unrelated in every of the other talks you have been listening. So I can run like C++, Python, Lua, Chalk language, and libpd, and many other languages in the same context. Everything can be, like this is a crazy dream. So this is like the conceptual thing that's behind this thing. This is how one of the ways you can render the whole thing. That is Chalk language, but that could be rendered, as you can see, in many other languages. The graphical part is rendered as a shader using GLSL. But well, what's going on like inside this Pandora box? You can literally just live code, just write code and execute code using any of the language you want. And everyone can, like every language can share variables, share context, share memory. So you can read from the graphics into the audio, audio to graphics, language to graphics, language to audio. Like it's a very crazy thing. So there are many versions. One that uses Chalk, GLSLs, and Open Frameworks. Open Frameworks running as a live Lua or Python script. There's also a Unity version. I'm not going to be, like we can talk more about this in the demo. We incorporated a lot of AI and machine learning stuff, so you can use rave things with any model you want. We created a Wakinator live codable object, which is one of the main things here. This is also on the web, so now the Wakinator can be executed live on the web. You just go to WebChalk and you can Wakinate whatever you want. So we have all this, many other algorithms. This is just kind of we have many tasks, and you don't need to download anything. You just go to the web and train your model and train this thing. And the final step here is that you can train and play. And that's the most interesting part for me, because I'm not interested in hitting generate and hear music. I'm more interested in playing music, because I really love to be in front of the audience. It's like one of the biggest pleasures I have. So I'm trying to use this in a live context. So this is like kind of the main output. You can train on the fly. So you decide like how many measures, beats you want. You train the model. The audio stream keeps going. Then at some point, the model starts working with you. Then you hit train again, and it could be automatized. So yeah, you just keep the beat. Everything is using this library, and you can perform with other musicians using Ableton Link, which is awesome. And yeah, already said this, it's a shared context, so everything is exposed as a global. So you can go from graphics to audio to any kind of model to text or whatever. So you can just type words and generate audio, and that data could be graphics or graphics to any vector, and then those vectors go to the audio or to words or whatever. And yeah, so we'll see this in a demo in the poster session, and gracias.
next up, we'll have Latent Space Explorer by Alexander Lenz and Sebastian Trump. And Alexander Lenz is going to be the presenting author.
All right, hello everyone. Thanks for having me. The Latent Space Explorer is a tool for interactively exploring latent spaces in generative variational autoencoders. It enables musicians to navigate the position in the latent space through various musical parameters currently derived from live audio input. In this manner, it provides improvisational access to the model's creative potential in their logic exploration. As you can see here, the first step is the feature extraction from the audio signal. The features currently include tonal ambitus, note density, RMS value, and some spectral information. These features are fed into a simple neural network where they are translated into a two-dimensional representation and are used to control the position in the latent space of a separate variational autoencoder. The model in the Latent Space Explorer can be trained to generate a specific position for a musical action. For example, playing high fast notes with low ambitus means position X, Y. To be clear here, we are using two separate neural networks. The first one is implemented in the Latent Space Explorer for encoding the musical information. The second one is the variational autoencoder. And presently, we are using a variational autoencoder that generates rhythms. But in theory, you could use any variational autoencoder that provides access to its latent space. As a rhythm generator, we are using the M4L rhythm way developed and presented by Nao Tukui in 2020. This tool is a Max for Live device optimized for real-time operation. And this means that rhythms are generated live. This figure shows the architecture of the variational autoencoder inside the M4L rhythm bay. The encoder on the left encodes batches from 3 input matrices, which represent onsets, velocity of onsets, and timing offsets from the given grid. Once the plugin finished training with user-provided MIDI files, it uses the decoder on the right to generate rhythm patterns. For every position in the latent space, which you can see here in the middle, there is one according rhythm pattern. Now to show you the whole picture, this figure displays how the Latent Space Explorer and the M4L rhythm bay work together. Part A is the encoder of the variational autoencoder. Part B is the decoder for rhythm generation. For training, you'll need part A and B, and for rhythm generation, only part B is required. And now, to generate rhythms, you could simply drag the XY position of the XY fader with your cursor on the computer, but that's where the Latent Space Explorer comes in, which you can see in part C, and it enables the control of the position in the latent space through musical actions. This is the graphical user interface of the Latent Space Explorer, which is also a Max for Live device. And so in summary, we propose a method for musical exploration of latent spaces using a separate exploration model to bridge the gap between musical actions and generated rhythms. And our initial experiments seek to glimpse the musical potential of this approach, which you can see at the poster stand later or online on the paper. Thanks for your attention.
And the last presentation today, in this session, is going to be investigation of live coding using a combination of ChatGPT and Finetuning GPT-3 by Tomoki Okuda and Kazuhiro Ryo. And the presenting author, you are Tomoki Okuda. Nice to meet you.
I'll be presenting our research paper called Investigation of Live Coding using a combination of ChatGPT and Fine-Tune GPT-3. This paper was authored by myself, Tomoki Okuda, and Kazuhiro Ryo. AI is currently transforming the world, but on the other hand, simply having AI output music in its entirety is a reproduction of past works and making creative expression difficult. For this reason, mutual interaction between human and AI is necessary. This study examines the combination of the GPT series, which is currently the most commonly used AI, and live coding performances that describe musical performances in text. First, we will fine-tune a GPT-3 specialized in code generation for live coding. For the dataset used to fine-tune GPT-3, we prepared a total of 998 pairs of source code and corresponding Japanese text that explains it. The flows of the performance will be involves the following steps. Firstly, creating Japanese prompts. Secondly, generating tidal cycles code from Japanese prompts. And thirdly, modifying tidal cycles code. To enable performers to better understand nuances of the language and design effective prompts, we adapted Japanese as a native language. As a result, efficiency of the performance was enhanced due to the ability to output a large amount of code in bulk. But since a self-created dataset was used, the generated output was to some extent predictable. So next, we will incorporate ChatGPT into the performance. The traditional tasks of creating Japanese prompts in step 1 and modifying tidal cycles code in step 3 will be replaced by ChatGPT. This is demonstration. Enter the Japanese prompts on the left side, and fine-tune GPT-3 generates the right side. And this sound was generated by ChatGPT. And paste the Japanese prompts on the left editor. And fine-tune GPT-3 generate the code on the right editor again, and performance continues. Yeah. As a result, compared to using only fine-tuned GPT-3, unpredictability has increased. However, this approach sometimes led to the situation where the performance continued to generate the same rhythm pattern as it progressed. So unintentionally causing a repetitive output. So next we will incorporate human ideas into the performance. To introduce diversity into the rhythm pattern, we'll generate the rhythms based on the performer's idea. The synthesizer part will be played by the performer, and for the drum part, following approach will be taken. In step 3, where the code is modified, synthesizer rhythm pattern will serve as a basis for the performance with ChatGPT modifying the code. As a result, when the performer describes a complex rhythm pattern, ChatGPT describes a slightly modified complex rhythm pattern based on the synthesizer drum pattern. By incorporating the performer ideas into the AI-generated performance, diversity emerges in the progression of the performance. Artists hold diverse views on how to perceive AI. When combining personal AI, fine-tuned GPT-3, and universal AI, ChatGPT, how should we interpret the nature of their interaction? I will continue to explore the way to re-envision AI as a collaborator in the future. Thank you for listening.
We have actually got one more presentation because I accidentally skipped over it, so I'm very sorry to the authors. As part of this is one of the main papers and posters, and it's called Emotional Machines. The authors are Jorge Forero, Mónica Méndez, and Gilberto Bernades.
Hello everyone, my name is Jorge Forero and I am completing my PhD in digital media at the University of Porto under the supervision of Professor Mónica Méndez and Professor Gilberto Bernades. The research project is titled Emotional Machines and focuses on bimodal speech-based recognition for effective virtual environment generation. In this scope, our guiding research questions are: how can we assess bimodal speech-based emotional ambiguity, and how can we define strategies to map emotional predictions into virtual environments? I will start by saying that an effective virtual environment system includes at least two components: a speech emotion recognition system and a virtual environment generator. Considering electrophysiological measurement difficulties and the fact that VR headsets hinder user faces, we propose to include a speech emotion recognition considering a bimodal machine learning architecture and a strategy to map predictions into virtual environments. Our contribution includes two models to capture emotions from semantic sentinel analysis and acoustic speech emotion recognition. Our outcome results have considered diverse architectures. In particular, for sentimental analysis, we adopted a Rocky classifier over the Gutenberg database containing poems labeled in two categories with an accuracy of 85% on the testing dataset. We also worked with a long short-term memory architecture trained with film reviews with an accuracy of 88%, and we are currently adopting a BERT-based pre-trained model fine-tuned with an emotional database containing 6 categories with an accuracy of 4% on the testing dataset. For the acoustic model, we analyzed a multi-layer perception and a convolutional neural network to predict polar motion with an accuracy of 75% and 81% on their respective testing datasets. Currently, we are using a long short-term memory network trained with a RAPTES actor-based database annotated within 8 categories with an accuracy of 89% on the testing dataset. The novelty is that after this differentiated bimodal analysis, we could access a way to understand and measure divergences in prediction for each mode. These divergences is what we call ambiguity. We could combine or fusion acoustic and semantic features to train a final layer, but we will be losing the inherent speech ambiguity because divergences are not necessarily errors in predictions. Thus, we propose to evaluate these divergences presented on a multimodal corpus using our bimodal model to assess words and sounds that increase or reduce ambiguity. So to the question, can we define a strategy to map emotional prediction into virtual environment? We propose a novel strategy to map a speech emotion prediction into virtual environment. To map emotion to music, we develop an in-depth analysis related to the association of musical parameters with emotions. We consider using the Livingstone musical emotion space to map each emotional category using the effective norm for English words, the NU. Predictions obtained are mapped to parameters such as harmony, rhythm, tempo, and timbre. We updated Concord software to create a rule-based music generator with long-term compositional consistency. To map speech to visual, we have followed 2 methods. With style transfer, we can create an image that will be used as a style for a second heterorectangle panorama. The second method involves image addition over a predefined image searched from Google Street API. Finally, we use resulting textures and music to create an audiovisual environment on the fly while speaking. Thanks for watching.
That's the end of our session today. So thank you to all the authors and presenters. Now is the time to ask questions, but not here. So just follow the general flow of people towards the poster session across the way.